Hi! In this video, we'll talk about subbases and then we'll introduce continuity in topological spaces. So it's a very generalized continuity. And so you can see now that when we generalize it, how topology plays a part in real analysis, because you can still talk about continuous maps between one topological space to another. And by understanding it in a topology, then when you shrink it down to metric spaces, later when we introduce it, you will understand it better. And so let's first go on to understand what is a subbasis. And before that, let's have a recap on what is a basis by proving this lemma. So we have seen how a basis generates a topology, and now we want to go the reverse direction, where a topology, we want to know what is the basis generating it. And so suppose C is a collection of open sets such that for each open set it has the property that of the basis that we want. Then we can just say that C is the basis of the topology. And to show this, we must show that it fulfills the two conditions, which is quite easy to see the first one, because given an X, since X is an open set of itself, it will contain an element C such that X is an element of C, which is a subset of X. And we're done. And the second condition is if X belongs to the intersection, then C1 and C2 being open, so is the intersection. And hence, by the hypothesis that any open set that will exist a C in the collection script C, we are done yet again. And so now we've shown that C is the basis. And then the next part, I'll leave it to you, but it's the same idea. We just show that this C generates the same topology as the one we want. And then we will be done with proving that C is a basis for the topology it generates. And so when we generate a topology using a basis, the basis needs to have certain properties. But now we don't want these properties, let's say, and we want to just describe it with just any given collection. But it must still have certain fulfillments before it can be made a topology. It can actually be made to give us a way of describing the open sets, and that's known as by taking the finite intersection as well. And so what it means that we call it a sub-basis. So don't be mistaken that it is a collection, a subset of the basis. We just call it a sub-basis, and it is generated to be collection of all unions of finite intersection of the elements. And remember, in a basis, the topology is the elements of unions of basis elements. Now we are saying that it's a collection of union of intersections between these sub-basis elements. And I'll leave it to you to read the check that it is a topology, because it is exactly the same as when we prove it for basis, but instead of having the property now, we just take a finite intersection of this collection of elements of this subset in the sub-basis. And the proof is very similar, so I'll leave it to you to read. So, and set is open if and only if for all the elements in the set you can find a finite subset such that X is the element of this intersection of the finite subset, and this finite subset will be a subset of U. So introducing this sub-basis now, we can move on to what we really is important, and that's the maps between topological spaces. And when we talk about the idea of topology, now we can introduce the notion of continuity when we have functions between two topological spaces. And we say that a function is continuous between two topological spaces x and y if all the open sets in y, the pre-image is open as well. And the pre-image, if you recall, is just the set of points in x such that fx is an element of v. And so we can see now that to say this is an open set in x, the continuity not only depends on the function f, but it also depends on the domain and range because of the topology specified on each domain and range. So we can say that f is continuous relative to the specific topologies. So let's just look at the example, and then more and more examples will build our understanding. So we have x that has the discrete topology, meaning all the subsets are the open sets. Then any function is continuous because if you take the pre-image, it will be a subset in x, and that is defined to be open, so it's definitely continuous. You can also show that the identity map is continuous, but of course when we define the identity map, when we say it's for x or x, these two must have the same topology. So any open set here, when it goes back, it will still be the same set, which then is open again. And then we can see that the metric space is open with respect to the metric space topology if and only if it's continuous with respect to the matrix. And you can just use the open set criteria for sequences as well. And we have already established the equivalence between all these three, and we can see that it is continuous in the metric space topology sense, is what we have proven last time from defining it first to be continuous using metrics, and this means the epsilon delta definition. But now we define here, we can again prove the epsilon delta because we already shown their equivalent. And so in analysis, we can reformulate this definition of the continuity, but of course epsilon delta won't make sense now because you don't have a distance function. But we use this definition of continuity of open sets in this arbitrary space, and we can again then use this definition, and it can prove certain theorems in our metric space which makes it simpler, and we'll see it in coming videos. So let's again now prove some basic notion of continuous function and show that they still hold true. And of course, composition of functions is still continuous because if you take an open set in Z, then this pre-image will be the pre-image of F of G pre-image of V, and we know this is open by continuity of G, and this is open by continuity of F, and hence G circle F is continuous as a result. And so why do we introduce the subbasis earlier in the video? It's because if it's continuous, then we only need to care about the sets in F in the subbasis, and then we can if a map is continuous if and only if for all the elements in the subbasis the pre-image of it is open. So we don't need to take all open sets now, but we just need to take the subbasis. And the reason, of course, is because the subbasis generated the topology. So all the open sets are somehow a form of this subbasis. And so if you can just show that the subbasis, the pre-images are open, then the map is continuous. And the proof is quite easy because if F is continuous, then of course, because V is an element of S which is open, then the pre-image will also be open. And then conversely, if we are given an open set in Y, it can be written as unions of elements in S. And so because pre-image respects set theoretical notation, the pre-image of V will equals to the union over this family of the pre-image of Vi, where Vi is the intersection, and then this intersection, finite intersection is open, and then the arbitrary union will also be open, and hence we are done in showing that this condition is fulfilled, that F is continuous. And lastly, we'll just introduce what is a homomorphism, and that is saying that if you know that F is bijective, then it has an inverse. And if this inverse and the original function are both continuous, then we can say F is a homomorphism. And so what you're saying is that F is a continuous function and its inverse is also continuous. So it just says that you can simplify it to saying that the inverse image of U under the inverse map is open in Y, but the inverse image of U under the inverse function is the same as U. So you can just like think of it. So it's open, it's bijective correspondence such that FU is open if and only if U is open. And this remark shows that it is not just between the sets but between the open sets as well, this bijection. And so such a property of X is called a topological property. And so when we give a homomorphism, we want to preserve not only the function itself, but we want to preserve the openness of the maps of the sets. So when you map into another set, you are still open. However, we like to take note of some important examples that even though F can be bijective, its inverse may not be continuous even if F is. So we can't say that a homomorphism is a bijective continuous map, because that will imply that yes, F has an inverse because it's bijective and F is continuous, but it may not be that the inverse is continuous. So it is really saying that F is continuous and bijective, and its inverse, which is continuous as well. And so here's an example of one where the inverse is not continuous, and that is the map defined to be ft, which equals to cosine 2 pi t, comma sine 2 pi t. So we are transforming this interval onto this disk. So F is bijective and continuous because these two portions are continuous and bijective, but the inverse is not continuous because the point 0, there will be no union, there will be no open set such that it won't cross over to the other half of the semicircle. So like you can think of it like this is your open set now, but this point is reached. So any set that contains this point must cut into this end of the circle, which is not within this open FU. So that means that the set FU is not open. And hence, this example is a good example of why an inverse may not be continuous even if F is. And so, we have come to the end of this video. I hope you have enjoyed it. And in the next video, we'll talk more about different types of topologies. See you.